Hello everyone, welcome to DSP NIT Andhra. In this video, we are going to learn the example 5.1.1 and 5.1.3 through MATLAB from Digital Signal Processing by John G.proakis. First, we are going to learn the example 5.1.1, which is the example of response to complex exponential signals, the frequency response function. The response of any relaxed linear time invariant system to an arbitrary input signal x of n is given by the convolution sum formula, which is y of n is equal to summation of k is equal to minus infinity to infinity h of k x of n minus k. To develop the frequency domain characterization of the system, let us excite the system with the complex exponential, that is x of n is equal to a into e of j omega n, which is in the range of minus infinity to infinity. The system is characterized in the time domain by its unit sample response, where a is the amplitude and omega is an arbitrary frequency confined to the frequency interval of minus pi to pi, which the response be y of n is equal to summation of k is equal to minus infinity to infinity h of k into a into e of j omega into n minus k, where a is equal to summation of minus infinity to infinity h of k e of minus j omega k into e of j omega n. In this above function of the frequency variable omega, this term of this Fourier transform of the unit sample response h of k of system, Hence we denote this function as h of omega is equal to k is equal to minus infinity to infinity h of k e of minus j omega k. The function h of omega exists if the system is BIBO, which is bounded input bounded output stable, that is summation over range of minus infinity to infinity magnitude of h of n less than infinity. The response of the system to the complex exponential is y of n is equal to a into h of omega e of j omega n. That the exponential signal in x of n is called eigenfunction of the system. The multiplicative factor is called as eigenvalue of the system. Complex exponential signal is a form of an eigenvalue of a linear time invariant system, and h of omega evaluated at the frequency of the input signal. Now we see the example of 5.1.1. The output sequence of the system with impulse response h of n is equal to 1 by 2 whole power n into u of n, where the input is a complex exponential sequence x of n is equal to a into e of j pi n by 2, which is in the range of minus infinity to infinity. First, we evaluate the Fourier transform of the impulse response h of n, and then we use to determine y of n, where h of omega is summation of minus infinity to infinity h of n e of minus j omega, which will occur 1 by 1 minus 1 by 2 e of minus j omega, where for this in this entire process we obtain the output response where y of n is equal to a into 2 by root 5 e of minus j 26.6 degrees into e of j pi n by 2, where final output y of n is equal to 1 by root 5 ae j into pi n by 2 minus 26.6 degrees, which is in range of minus infinity to infinity. Now we see the MATLAB demonstration way of 5.1.1. Now we are going to refer the 5.1.1 example through MATLAB, where given signal. Generally, the signal ranges from minus infinity to infinity, but in this example, we consider n to be in the range of 0 to 100. Now, the function h of n can be defined as 1 by 2 whole power n, and that can be the impulse response of the uh, impulse response of the example that can be given in the example question. Now, the input response function x of n can be defined as the exponential of j into pi into n by 2. Now, the desired output function y of n, which we achieve, is 2 by root 5. Root 5 we can write as 2.236 into exponential of j into pi into n by 2 minus 0.46425. 0.46425 is a radians to the 26.6 degrees. Now we can see the uh, signal spectrums of these inputs that can be given in these conditions. Now figure 1, the we can shows that the h of n, which is impulse response of the system, where figure 2 can be shown that the x of n, that the input response of function, where magnitude, phase, real part and imaginary part, that we can show from in the plots. That for magnitude, the abs abs of x can be defined, and for phase, angle of x can be defined. For real part, real x; for imaginary part, mag of x. In figure 3, the output we can show in magnitude, phase, real part and imaginary part. Now we can see the output response of the program h of n, which shows the um, ranges of n from 0 to 100, and this can be shows the h of n plot signal spectrum. Now, x of an input response that we can choose the magnitude of x, phase of x, real part of x, imaginary part of the x, where entering is 0 to 100, where this is the magnitude, this is the phase, this is the real part, this is the imaginary part. This all shows that the x of n signal spectrums. Now we can see the y of n signals, that magnitude, phase, real part and imaginary part, where the n signal ranges from 0 to 100 for all these parts of the um, function. This can be shows the magnitude, phase and real and imaginary part of this graphs. Now this is the example of the 5.1.1 in MATLAB demonstration. Now we can proceed to the 5.1.3 example. Now, the example 5.1.3 is the response of the system in which the example 5.1.3 to the input signal of the x of n. H of omega, or magnitude of h of omega and phase omega, completely characterize the effect of the system on a sinusoidal input signal of any arbitrary frequency. Magnitude of h of omega determines the amplification of mod h of omega greater than 1, or attenuation magnitude of h of omega less than 1, imparted by the system on the input sinusoid. The phase omega determines the amount of phase shift imparted by the system of input sinusoid. H of omega specifies the response of the system in the frequency domain. It is called frequency response of the system. Magnitude of h of omega is called magnitude response, and phase omega is called the phase response of the system. Input to the system consists more than one sinusoid, the superposition property of the linear system, to determine the response. Now we see the mathematical example of 5.1.3. The response of the system example of 5.1.1, which is h of n is equal to ae 1 by 2 whole power n u of n. Now given response x of n is equal to 10 minus 5 sin pi by 2 into n plus 20 cos pi into n, which is in the range of minus infinity to infinity. The frequency response of the system is h of omega is equal to 1 by 1 minus 1 by 2 e of minus j omega. The first term of the input signal is fixed signal component corresponding to omega is equal to 0. where h of 0 is equal to 1 by 1 minus 1 by 2 is equal to 2, where the second term we put frequency pi by 2, the frequency response of the system will be h of pi by 2 is equal to 2 by root 5 e of minus j 26.6 degrees. In the third term, the frequency omega is equal to pi. At this frequency, h of pi is equal to 2 by 3. Now the entire response of the system out to x of n is y of n is equal to 20 minus 10 by root 5 sine pi by 2 into n minus 26.6 degrees plus 40 by 3 cos pi into n, which is in the range of minus infinity to infinity. Now we can see the 5.1.3 example in the MATLAB demonstration.
Now we are going to refer 5.1.3 example through MATLAB. Generally, the signal n ranges from minus infinity to infinity, but in this example we consider n to be in range of 0 to 100. Now the function h of n is 1 by 2 whole power of n, which can be taken from the response of 5.1.1 example. Further, now the input response function x of n should be 10 into 1 comma 100. That once 1 comma 101 be taken because length should be finite. We taken from 1 to 101 paths in x of n minus 5 into sine into pi by 2 into n plus 20 into cos pi into n. Now, the desired output function y of n which we achieve is 20 into 1 comma 101 minus 10 by 2.236, which is root 5, 10 by root 5 into 5 into sine into pi by 2 into n minus 0.4642576, which is radians 0.464257.6, which is radians of 26.6 degrees plus 13.33 into cos pi into n. This is the conditions. Now we can plot the impulse response, input response, and output response. Now we plot the impulse response, which is labeled x labeled as n, y labeled as h of n. Now plot the response of input sequence, which is x label of n, y label of x of n. Now we plot the output sequence, which can be x label as n, y label of y of n. Now we should run the program. Now see the output responses of the signal sequences. H of n. This should be the impulse response that we can consider in the 5.1.1 example that we can be taken. H of n should be the impulse response that we can be considered in 5.1.3 example to get the desired output. Now the input sequence x of n that can be given in the example question, that the signal spectrum sequence that can be occurred like this. Now the desired output function y of n which we can achieve the signal sequence that should be occurs in this type. Now we can compare this input of the system consists more than one sinusoid because the superposition of the linear system determine the response, because this example can be referred in the superposition property. Thank you. This is the MATLAB execution of 5.1.
Now, the reference of this example is Digital Signal Processing in fourth edition by John G.proakis from the example 5.1.1 and 5.1.3. Thank you.